from lunch break. So before lunch break, we talked a lot about like interpretable models in terms of like the simplicity of the model itself, like linear models mostly, right? And like some unfortunate excursion into decision trees, right? Like, but anyways, so now we actually look at the other end of the spectrum. So how can we actually analyze a model without like having to know the model itself, right? Like, so what a model itself is. And that brings us towards model agnostic interpretations, right? So in general, we will focus on model agnostic post-hoc interpretation. So basically meaning after the fact that we trained the model already, right? So how can we actually analyze what's happening in there? And the key advantage of this method is that we can actually apply this to any model, right? So it doesn't really matter like if this is a complex neural network or like some GAM or like any other SVDs or whatever, right? So we can apply this kind of like this approach that we're going to talk about like to any of these models, right? And it also even allows us now, for instance, to compare different models for their interpretability. How exactly? So like a little bit, to give it a little bit away already, is if we actually find an interpretable method, right? So we can see that this interpretable method aligns more with the one model than the other one, while both of them perform the same way, then chances are that one of them is more interpretable than the other, right? Like, so this kind of things. The second thing is we will distinguish here between global and local methods. So global methods describe the average representative behavior of a model, and local models focus just on individual examples, right? So they focus on individual like predictions or like samples that we're going to look at. Locally with a linear model, right? Like with something more interpretable, but there's also something that's called rules or like counterfactual explanations and Shapley values, right? And Shap basically being one version of how to compute those Shapley values. So the idea there is that we're going to talk today or now still about line, and then later in the lecture series we will talk about like counterfactual explanations and Shapley values in particular. Again, the idea here for local models is if we have our model and we actually predict now something, or like we actually produce some output, be it the class or like whatever, right? We actually try to investigate or like assess like locally for this one particular sample if we can analyze what led to this classification, generation, etc. Right? So locally, and then in terms of like how this could be applied in let's say in a decision-making process, we can then offer these local explanations to human experts, for instance, and the human expert would then make the decision, right? And for like all of these approaches above, including the black listed ones, I highly recommend Interpretable Machine Learning by Christoph Moiner, which is an online book, free available for everyone. So this is great literature. In terms of global methods, there's things like partial dependency plots, like accumulated local effect plots, so to say. They're the idea that we analyze individual features, but like we make this actually in a cumulative way. Also feature interactions, so so-called H statistics, where we measure basically like how much the contribution of the joint effects of these interactions is, or these features is. But also like other approaches like functional decomposition, permutation feature importance, and global surrogate models. And in this lecture, well, and finally prototypes. In this lecture in particular, we're going to look at permutation feature importance and the general, like very, very general perspective on global surrogate models. And then later down the line this week, we will also talk about prototype models. And here the idea is, again, that we have our model and we produce something, right? We generate something, would be classes or actual like some samples. But then instead of looking like only at individual ones, we look at a representative set. So it doesn't mean that we need to look at all possible outputs or whatever, right? But we look at more than a single output, right? So there's, in addition to the previous step, there's something like a pick step, right? Or a selection step. And then we try to make sense of this group of decisions, right? Like rather than individual decisions, right? So that's the perspective here for this one. So we're going to start with, and again, like Christoph did the great work here with this ebook. So like, yeah, have a read. Yeah, so we start with permutation feature importance. The idea, as the name already suggests, is basically that we can estimate the importance of a feature by calculating the model prediction error after and before messing with that feature, right? So basically, like one of your colleagues asked me like before the break, so you said that performance measure is not a good measure, right? Like for explainability. But what if we actually use it as comparison? So if we see like, oh, how well does it perform now, or how well perform does it, like for instance, with the feature, like I think the example was the background, with the background feature or without the background feature, right? And this kind of would be the like approach that does exactly that, right? So we actually do use the performance measure here, right? But comparatively, based on the features or the feature permutation, in order to make an assessment how important that feature was for the overall prediction, right? So the idea is that if it actually increases the error, right, then like the model actually relied on that feature, so it required it to perform well. And if it does not increase the error at all, then chances are that this feature is completely unimportant, right, or plays no role. Bless you. Okay, so the original idea came from random forests by Rahman et al. In 21, and was later on and also established. Not 21, in 2001, it was later on extended. So let's look at this a little bit more formal, right? So if we have our trained model, again, like I try to be consistent, but throughout the entire like slide deck and like following slide decks, if we have a head that refers to a pre-trained model, to a complex model that was already trained on the data, right? So like the training for this one is already finished. So we have our trained model, right? And we have like the data points that, for instance, it was trained on, like the feature matrix X, right? Including the target vector Y's. Or target vector Y, right? So like the labels or whatever. And we trained it with respect to some loss measure, right? So this could be mean squared error, could be, but also something else, right? Like if we, for instance, train it in a more distributional way, right? So this could be maximum likelihood and so on and so on. So now the idea is that we go step by step for each of these features, right? So like we have M features, let's say, right? For each of these features, we generate a new feature matrix where we permute that individual feature. So we take the same data as we had before, right? But now basically we take just the feature instances that we had. So for instance, for all our data points, like let's say the third feature, right? And we just like randomly scramble it and attach it back in, right? So first question, why do we randomly scramble it instead of just making up values? First question, do you understand what I mean when I say we scramble it? Who does not understand what I mean? Okay, so like enough people for me to draw something on the blackboard. I don't know if you've noticed already, but I love drawing on the blackboard. So let's say, for instance, we have, let's do this. Let's say, for instance, we have now like our data set, right, capital X, and each row in our data set is now like it's basically one data point, right? And then we have, let's say, like some values here, right? Like it doesn't really matter. Like we have all these values, and we have like this feature. This will be feature one. Let's do this by one, right? And this will be by n, and then we have here phi n. Okay, so we have all the values here. And what we do is now we take basically these values, right? So this one basically would be x1m, or like phi 1m, right? Because for the first data point, we have phi 2m, we have phi 3m, and so on, right? So because this is the first data point, the second, the third, and so on. Does it make sense? So instead, what we do now is basically we create our permuted data set, xperm, where we maintain all of the features that we don't want to investigate right now, but for the one that we actually care about, we just randomly permute, right? So we basically say, for instance, 2m, here we're going to put 3m, and here we're going to put 1m. Does it make sense? So we maintain the values that they had, but we just like change the order randomly in our X data set, right? So, and you want to answer why we do that?
Oh,
Okay.
I mean, I can warn, but
No, but like us.
the red chalk is barely visible on the board.
Oh, okay. So, okay. Good point. That is something that you're always to just like throw in there. You don't need to lift your hand for that, right? You basically just say like, red chalk is not visible, or you're too not loud enough, or whatever, right? Because that actually, what is with this red chalk? Like, do we not have? Okay, through the red chalk. We're not going to do red chalk anymore. Is that better?
Yes. Yep.
Okay. Green on green background is better than orange and red. Okay. But I agree, it is weird. Like this is what's the one there? Now you only would have like need the ability to read my handwriting, but that's nothing that color will change. Okay, so but does it generally make sense now? Like, okay, so now the question, why do we permute instead of just making up numbers? Why don't we just like say, okay, instead of this one, we use 0.75, right? And instead of this one, we use 0.88 or 89, right? Or this 0.01, right? Why don't we just make up numbers?
And that will change the distribution of this feature.
How valuable, like, yes, it would, right? But how valuable is the distribution of the individual feature in the first place? I mean, we're talking about the marginal distribution of just one feature of like the entire like row, right? Like, so, yeah. But it is exactly that, right? Like, that is the issue. And like, the question is not about how valuable it is to know this distribution. The question is rather of the model that we try to analyze has ever seen values in that range, right? So because if I try to analyze what happens if this feature is, or if I want to analyze how important this feature is, and I just pick a value of like 0.5 or like minus 5,000, right? That the model has never seen for these values of the feature, that like only tells me really like how like sensitive it is to this like change in the feature, right? But not really like to the feature itself, like because it sees now suddenly something that's completely unrealistic that has never been trained on. So we're like not only OOD, we're like super OOD.
And would it work to set this feature to one value for all the data points? Maybe a value that we select based on the values that are already there. For example, the mean of all of them.
I mean, like you could. So first of all, it's not even clear if the mean actually appears, right? So that's an assumption. But the other thing is like, so what we gain, right? So like, what we gain by doing that? And the second thing is also like if you have it everywhere and you want to actually see like how important that feature is, but you take basically the average, right? Then like maybe the feature is super important, but the average like just contributes an average amount to it, right? And now it basically always contributes everywhere in the average amount to it, right? So it's, yeah.
Is it also possible to generate new data with the same distribution and same mean and everything the same, but completely new data? Would it make any difference to use the same values and shuffle them?
Okay, when at which step do you want to use the new data? Do you want to generate new data and then still permute the
for the future? Because currently you're just shuffling all the values, but still use the old values. But would it make any difference to use like new data for this data points for this feature?
So that would be a problem because this would like if you generate like realistic samples and so on, right? Then also the feature itself basically coincides with the other values, right? So it would still be something that, let's say, if the feature contributes to certain interactions in a certain way, right? Or there's like some underlying correlation between this feature and like other features, they would change together, right? So you would still only produce basically features that make sense or feature values that make sense at that step, but it doesn't allow you then to introspect what happens if we mess up the feature and use values that don't make sense in this combination of the stream. Does it make sense?
Yes, thank you.
Okay.
In the case of taking the mean, that could also transmit information. Like the
Mhm.
model, the mean could be a feature by itself, but the model somehow extracts and uses. So if you would just use the mean, you could still provide the feature to the model.
That could be true, yes. Like, I mean, I wouldn't know how it would, like, the model internally would produce the mean of this feature, like, at any, like, inference step, because it only ever gets that one data point, right? But it might have, through the bias or whatever, internally, like, learned what the overall batch mean was, or something like this, right? Yeah, so that could be the case. Okay, but anyways, back to this one, permutation. Everybody understands what we're doing, okay? So we're permuting this, and that basically breaks the association between this feature and like the overall like outcome that it produces, right? So basically, we still have a realistic value for this feature, right? Because we've seen this in our data set before, but we potentially have not seen it in this combination in terms of like correlation and interaction with the other features, right? Does this make sense? So we would naturally assume that if it's like a relevant feature, right, a very relevant feature, that this would significantly reduce our performance. Whereas if it would be completely irrelevant, our performance would be the same no matter which of those values like we chose. Make sense? Okay, excellent. So, and we can now basically choose our loss like in two different ways, right? So, or like multiple ways, like two very common ones. It's either like a relative performance measure or like feature importance measure, which would be the quotient, or like a more like absolute one, which is the difference between the permuted performance and the ground truth performance, right? And then afterwards, we just sort the features descending by our feature importance, and that gives us a list of like the most important and least important features, right? So, and that's all there is to permuted feature importance. That's all of it, really. So the question now becomes, though, like, what do we compute the FI on, right? So the feature importance on the test set or the training set. So who thinks we should train it on the test set? Or not train, sorry. We should evaluate it on the test set, and who thinks we should evaluate it on the training set? So who's test set? Okay. Who's training set? Who's I don't care. Oh, boo. Okay, good. So like it depends, right? So if we compute it on the FI, right? Like you could argue that, hey, it depends actually on the error measure, right? So and in this case, the error is like trained on trainings, like on the test set. So like evaluating the error on the training set is kind of useless, right? Because we're basically like ideally have 100% success rate, right, on a training set. So we should use it on a test rate, on a test set, right? Because this is the error that actually also speaks towards generalizability and the actual performance of the model, right? So basically saying this term here, like where's my cursor? Let's do pointer thing again. So basically this part over here only makes sense on a test set, not on a training set, right? So having this going into the FI is kind of pointless, we can argue, right? So we should train it on a test set. There's a counter argument already.
Yes, ideally you will do it on validation set.
Yeah, okay, so
Selection.
Sure, like, but I think like the arguments hold also for the same against the train, like, so basically at this point we're arguing against the training set, right? So if you like the same arguments hold, if we so the argument was like, oh, you should do it on a validation set, sure, right? But like, but there's an argument against that. There's an argument actually, or several ones, like why we should do it on a training set, even though that this term here on the training set makes no sense, right? What we're trying to evaluate is how well our model actually perform, like, or how much our model actually depends on that feature, right? So we're trying to evaluate, like, based on the training set, so what the model actually has learned, right? Is what the model has learned, like, relevant, right? And the learning happened on the training data set. So we should also permute the training data set in this case, right? So like, so this would be the counter example. And the thing is, ideally, you just do both, right? You can do both, and then like see what kinds of interpretations you have. But it's just to show you that it's not all just black and white, right?
depend on the purpose?
I mean, yes. So like it depends what you want to show, right? But again, like if you go through the steps of doing this anyways, right? Like so you can kind of like only select one of those two options, but I think both options offer insights independent of the purpose, right? So there's maybe something that you want to show, right? And then you figure like focus on that one, but nevertheless doing both shows you something, right? So you might actually gain like additional insights there. Okay. So pros and cons. The advantages, it's like nice interpretation, right? So like the FI actually tells you like how relevant this feature is, right? And it's like a highly compressed global insight into the model behavior, right? So like it's like literally breaks everything down to just like one model, and it's like very simple to understand. We've done this just with text on a couple of slides, right? So it's very easy to understand how this method works. The disadvantages are that it requires the ground truth data, right? So we actually need to know what the true labels are and these kind of so we need access not only ground truth data but the ground truth data set that we're trained on, right? Or the test data set if we have one, but we need that, right? And the results might vary like strongly depending on how much you permutated, right? Yeah, so like basically this is like a random process. Sometimes you just by accident end up in situations where the features are closer to what they've really been and so on, and sometimes we're not, right? So this is what this means. And then it can be biased by unrealistic instances. So the idea is that even in this case, the values are realistic, right? Because we've seen all of these values before. But the problem might be that, again, due to correlation or like interaction, right, there is like this combination of feature 1 and feature 2 of like the other data point never occurs really, right? So we're creating this kind of like Frankenstein data points, right? And that might actually like be completely nonsense. So the model might be really, really good in doing its job and like might even have like good reasons for doing it, but we tested it on something unrealistic, right? So that's kind of like the downside. So questions about this before we move on? Okay.
The last thing is, for example, when some variables depend on each other.
Or have common dependencies. Right. So the remark was like the issue with this unrealistic features happens if the features depend on each other or like have the same dependencies. Yes. Okay. So the next approach are global surrogates. Also something that we can just break down on a couple of bullet points, right? So they're arguably even simpler than permutation feature importance, right? So the idea is like we select a data set X, right, or X, and then we can basically like we train the complex model on this thing, right? But the predictions on a complex, we get the predictions on a complex model, and then we pick an interpretable model that we use as a surrogate. What it means, and we're going to draw it on the blackboard in a second, is that we're trying to find now a simpler model, right? Like an interpretable model that explains the complex model, right? Or like the behavior of the complex model. And then we interpret what the surrogate model decided and assume that the same argumentation is true. So what can this potentially look like? Let's do, again, the blackboard thing. So we're going to do something very, very quick here, right? Because we want to save some time, and that's really, really like simple problem. We're going to go back to our let's say we have like some positive, like some negative examples, right? Let's do X's and O's. Let's do not X's. Let's do triangles and circles, right? We have triangles. We have circles. We have triangles. We have circles, right? So this looks very much like our banana example from decision trees, right? But let's say for now we learned a very complex model, not in red, let's try yellow, right? That basically like draws a line kind of like this. It says everything on this side of the line is triangle, right? And everything on this side is circle, right? So this is our overall model, right? So it might actually not even be perfect, right? So it might be even something like this, right? So, or actually, let's do a rather like that, right? With the application in this direction. So this would be our complicated model. We don't know like the decision boundary here, etc., etc. But what we can do is like we can now basically have our data set. We get our predictions, and in fact, in this case, the prediction would be wrong, right? In this case, the prediction would say triangle, even though it's a circle, but it doesn't matter. We're not going to compare it to the ground truth. We're going to compare it to the prediction of the model, right? So if we're now basically build our decision tree in here, which would be an interpretable representation, we're just going to build a decision tree that matches the prediction of our global, like of our complex model. So in this case, for instance, we could get away with just like 2 splits, right? Because this part here was classified by our complex model as a triangle. And with this, basically, we like use this interpretable model and then see like, oh, okay. So what the complex model seems to do is first determine like the width of the object or whatever, right? And then later on in the second step, like something about the height, right? With slight deviations. And this gives us then the ability to interpret our global, like our complex model, like on a global scale. Does this make sense? Okay. And that's all that is there basically in these bullet points. Okay. So some pros and cons, right? The advantages here are that it's like very flexible and like an interpretable method, right? Like, so you've seen this is very easily doable, very quick, like, right? It's fairly intuitive. Hopefully you understand or you agree with me. There's like, I didn't put the R squared earlier, but we can actually use, for instance, like the R squared loss or like squared measure in order to see how well the, like our interpretable model actually covers the global model. Oh, sorry, I keep saying global, the complex model, right? So we have like something measurable there. The disadvantages are that surrogates never sees the ground truth, right? So a surrogate is based on the labels from the model. So if the model itself is actually really, really bad, then we might have a way to interpret it, but it will interpret something very, very bad, right? And then it also inherits all the disadvantages of the surrogates, right? So all the problems that in this case decision trees have, we will also have there, right? So maybe we think that we found a good decision, right? Like in the sense, but the fact is actually our interpretation depends heavily on the threshold, and the threshold might be too fragile at this point, right? So these kind of cases. Okay, any questions about global surrogates before we move on?
Do we have to fit it the prediction to the 100% accuracy, for example? Or if we don't fit it, then we lose.
You might not even be able to do 100% accuracy, right? Because like the thing is like that, like depending on what your interpretable model is, if it's for instance even just a line, right, then you will not be able to do it necessarily, right? So yeah, so you don't have to, like, it has to be something that you're happy with. And again, this is something where R squared comes in. So you can actually afterwards with R squared measure how close you are to the model in terms of prediction between the between the surrogate and the trained model, right? And then make a like decision based on that. Like you have like R squared value that is good enough for you, right?
So basically, it's limited in the amount of interpretability with the surrogate, with the local surrogate.
Yeah, so like your surrogate basically, or the limited interpretability that the surrogate offers, right? Like, I mean, like, you're always subject to that, right? So like, I mean, this is the lower point that it always inherits the disadvantages of the surrogate. Okay. Oh, yes.
So just to wrap, so we use the decision tree to explain the more complex model and compare the prediction selection.
We train the simple model on the predictions.
The prediction of the complex.
Yes. We don't train on the ground truth data, right? So we don't take the actual Y labels, right? But we take the predictions of the model. Because we're not interested in fitting a simpler model on the data. We're trying to fit the simple model on the complex model, right? So if the complex model does a misclassification, as in this case, for instance, right, then the surrogate should also like represent that, right? Make sense? Cool, good questions. Yes.
How can we make sure that the surrogate model uses the same features?
So how can we make sure the surrogate model uses the same features? Yeah, I mean, that's part of your model design, right? Like, so that's like the features that you, in this case, for instance, give to the decision tree, right? You will only be able to explain the model based on, like the complex model based on those features. So even though the complex model has like other features that it derives internally, right? You will still be limited to whatever you provide, right? So you don't actually have any guarantee or even like the necessity to use the same features. You could even argue that the moment where you restrict it to the same features, you're not model agnostic anymore. Right? Okay. Or not necessarily model agnostic anymore. Okay. Cool. No. Continue.
Where we have to assess the original model in order to get a good approximation with our spread model?
So the question is, where do we have to assess the original model in order to get a good approximation of our surrogate model? I'm not sure what you mean with where.
Where the feature space. So, for example, if we want to, we said that we need to create some predictions from the original model.
Yeah.
But what kind of, or where, what data that one can use?
Ideally, the most representative of your like actual trained on and tested on data set, right? So like in this case, for instance, you could say like you take the same data set that you trained the model on, and basically like or the one that you tested it on, like in this case also, right? Similar discussion as with the FI, right? But you always want to have like a data set that is representative to that the complex model actually learned how to deal with, right? Because otherwise it's just like unfair or like even not nonsensical. Okay. Very good, very good. Nice, good questions, a lot of questions. Like you should have saved some of them for the 5 and 5, but you will learn, young Padawans. Okay, so next we're going to talk about the local interpretation or locally interpretable model agnostic explanations, short LIME. So yeah. So talking about LIME, I was just informed that today there was again limette spaghetti in the cafeteria, which does not contain any limes. So that's a different type of explanation that people should talk about. But like, yeah, welcome to the mess. Okay, so yeah, back on topic, LIME. So instead of training the global surrogate, right, LIME focuses on like individual samples, right? Again, we're now in the domain of locally interpretable models. So we talk individual samples and try to find an explanation based on the features on this individual sample instead of for the whole data set. When does this come to play, right? So let's start a little bit with some formulation first. So let's say we have an explanation, like this is our explanation, like phi x, right? Which is the argument of a family of, for this, and x in this case is one individual data point, right? This is the data point that we care about, the local data point, right? And then we have a family of linear interpretable models, right? And then we have our complex model, f hat, as I mentioned originally, it will always be f hat. And we have like this one particular instance of the model that we're currently looking at, right? So, and finally, or almost finally, we have something that is a locality measure, if you want. So that why this becomes important, we will see in a second, but this is something that tells us basically how local our data points are, right? Or the certain points that we look at are. And then we have something like the final loss term is just something in addition as a regularizer that tries to maintain like the simplicity of our interpretable model, right? The idea is because if I have a family of linear models, I could just have one with 2 million like features and so on, and that's like kind of pointless, right? So we kind of want to, if we have a good solution for one with 3 features or one with 20 features, we would prefer the one with 3 features, right? So that's kind of like what this additional regularization term here takes care of. Okay. So for instance, as a loss term, we can basically just take the mean squared error between the complex prediction and our local surrogate prediction, right? G x z. And as a distance measure, we can just use the exponential map of some distance, right? So like whatever distance measure makes sense for your feature space, right? So this could be like Euclidean distance, but it could be also Mahalanobis distance or any other distance measure that you want, d, right? And then basically exponential map around that. So that's basically the locality measure there, right? And so Z represents the perturbed data points generated around X. So if we have X and we create new data points, so we push X a little bit around, right? And those are our Zs, okay? So we basically artificially create a new data set around X. Make sense? Yeah, and this is just like by introducing something for sparse features. So, and again, like for instance, this could be by introducing additional regularization terms like L1 or whatever, right? So something selective. So how does Lime work? Again, step-by-step instruction, select an instance for which you want to explain like your black box prediction, right? So, and then perturb your data set and get the black box prediction for this data set, right? So you basically take your X, you push it a little bit to the left, to the right, like every feature a little bit, right? And then predict your model explanation on that term, right? And then you basically say not all the data points are equal, but the ones that are closer to the original ones are more important, and the ones that are further away are less important. We're going to see all of this in a second on the blackboard, right? And then we train whatever interpretable model we care about on this newly generated data set, right? And by explaining now basically this data point with this new line, that gives us our overall interpretability. So let's do this on the blackboard together on an example. Again, no red. Maybe blue. Try blue. Okay. Okay. So let's say, for instance, we have like some decision boundary already, right? Like, so this is some model that we have, and we basically, like, so this is what we trained on, and everything in here is just quickly gonna shade it. Everything in here is green and good, right? Everything here is blue and evil. Like, can you see blue? Is it distinguishable? I'm very limited in the colors that I have available, people. Okay, come on. Okay, so maybe it's time for symbols then instead of color. Oh, okay. We can start a petition, like buy a new chalk for Rudy. Okay, so we say like positive. Let's stick to Greek. Okay, we have positive, right? Samples. And we have negative examples. Just gonna use minus here, but still blue, right? But all of those are basically our real data points, right? That we have. Okay. So and now we basically have a new point of interest. So we basically say like, oh, we actually have now this one, and we want to see this is a plus, right? But we can make somehow locally sense of this yellow plus, right? So what we do is we start generating our perturbed data points, right? So we generate them. So we basically push our plus a little bit to the right or up and down and so on, right? And directly classify it, right, with the model. So we directly use our complex model on this data point. Make sense? So basically, for instance, we push it a lot, right, to this side, and then we basically create a new minus data point, right, because it's below our decision boundary. We push it a little bit to the right, and have a new positive one. But not only that, we then also use our exponential map, right, to weigh the closer ones stronger than the further away ones. So for instance, we're gonna do this like it's a very thick plus, right? And this is still a very thin minus, right? The same if we perturb it to this direction, we have a very thick minus here. We have a very thin plus over here, right? If we add it like these guys, and then like this over here, that one, that's something medium, plus, right? Like, does it make sense? Right? This is what we're doing. So now, just based on these blue data points now, in a weighted linear manner, right? So basically taking the closer ones more into account than the further ones, right? We're gonna see now if we can find like something simple interpretable based only on those new data points, right? And this could, for instance, here be just a straight line. So, right, so we have basically this almost straight line. Let's assume it is. Just like a linear model. And with this one now, we can basically see, okay, now we have a linear model, and for this local point, it does a very good approximation on what is important for this one particular sample. Does it make sense? And that's what line does. I don't know, can you actually see the whiteboard? I don't want to break anything here. Okay. But yeah, so that's all that line does. Does it make sense? Okay, excellent. So here's what we just done on the blackboard now, but like in a dynamic way on the, or not on a dynamic way, like on a static image here. But like if you followed the whole thing on the blackboard, this should be like also understandable for you now, right? So with the linear model, of course, we can again check now how much each features were relate, right? Like so, like which features were relevant for this one. And again, this line makes sense. This line might make sense for this data point, right? But only at this data point. If you do it over here, it will be disastrous and wrong, right? So that's why it's local, right? Like this question.
Let's say you have a one-dimensional feature vector.
Yeah.
And you do this, and then you get 10 features that locally influence the decision. And then you have a 10-dimensional decision frontier. How is that interpretable?
Well, if your features themselves are interpretable, right? Because again, like you don't necessarily have to use the same feature as your complex model, right? Like you can have like something different, right? The complex model might have learned features and all these kind of things, but if you just go based on age, weight, height, like whatever, right? You can make classifications based on that, right? So that's the idea. Like and this is one of the downsides, right? So the interpretability here again basically depends on the interpretability of your linear model, like all of your surrogate. So if you have a surrogate that like isn't really the best one for interpretability, right? Then that's just that you will suffer from. Make sense?
So you have to weigh between accuracy and this.
Sometimes, yes. But again, like it might be that, for instance, in this case, right, like you don't care about all of the complex model. And it might be that, in fact, in here, that it is a very straight line, right? That it is very linearly dependable for this one decision making, right? Because you have like, again, like with the, imagine the XOR case. If I only care about the banana on the top left or whatever, right? I can draw a line because I don't care about the bananas on the bottom right, right? We have to talk about bananas here, but like, yeah, but you get what I'm saying, right? Yes, okay, great.
Features of the complex model might be different than the features of the linear model. Could it be that I'm interpreting completely wrong? Like I say, it only depends on feature A, but the model gives feature B or whatever.
So if you give, so the question is if the model is more complex than the simpler surrogate, right? And like it depends on different features, right? And like then the surrogate might do something completely off, right? So that's like the question there. And the example was if like surrogate depends on feature A and the complex model actually focus on feature B. So again, the thing is that this is kind of what you like the trade-off, not necessarily the trade-off, but like what you're trying to do here is to to have the surrogate that does leverage. In this particular case, for instance, if we have like linear models that does leverage some interpretability of the features as you give it, right? In fact, like you will almost never have the case when you have one of current complex models, like a deep learning model or something like this, that you will work on the same feature space as this as the surrogate does, right? Or the surrogate will work on something else, right? But the thing is, what you can do, right, is for instance, say like if you have some manual features, right, so that like that you're able to see how good does the local surrogate, right, perform given those interpretable features, right, like in comparison to the complex model, right? So or rather, or actually differently, it's not so how much do these interpretable features explain the performance of the complex model, right? So it's not necessarily like that you need to have the same features. Is that clear to everyone? Okay, cool. Nice. Yeah, and with this we're pretty much at the end, right? So we can actually extrapolate this. towards images and so on, right? So like just some examples from Ribeiro et al. In 2016, where they basically use this linear or like the simple surrogate models to interpret or like to explain different aspects of the image, right? So for instance here, like the guitar and so on. So the advantages, again, explanations are short, selective, and possible contrastive, which is nice, right? So it works for tabular data, text, and images and continuous data. So this is also amazing, and can use other features than the original model was trained on. There you go. It's even on the slides, right? And the disadvantages are that the complexity of the explanation model has to be defined in advance, right? And the instability of the explanations, because again, I learned this based on this one now, right? But if I perturb it a little bit more or less, right, I might end up with a very different line. Does it make sense? Okay, cool. So with this, we're at the end of this block, and it's time for a 5 and 5. Let's do that.